So next talk is by Stefano Anselmi, who is going to talk about the challenges of using Baryon Acoustic Oscillations in cosmology.
Thank you very much, Leandros, and thank you very much to the organizers for this very nice conference and for the invitation and for the opportunity to discussing with you what I've been doing the last years. So today I will discuss the challenges of using Baryon Acoustic Oscillation for cosmology. This work has been done in collaboration with several collaborators in the last 10 years. So what is the outline? So in cosmology, when we talk about Baryon Acoustic Oscillations, in general, we mean late-time cosmology-independent accurate distance method. So we'll discuss today the relevant challenges given this ambitious goal and their implications. Then in the end, I will discuss new proposals to address some of the challenges. So what is the goal of the video distances? So the goal is to constrain cosmological models, in particular the KNG time, and to play with consistency test, in particular what goes under the name of cosmological tensions. How? We do this by combining the video distances with other cosmological observations. In this way, we can reduce the genesis among parameters, we can break the genesis, or we can use video distances alone, for instance, to detect dark energy. I will explain you what that means. So here are just a couple of examples, so to show you how VO are crucial and relevant. So in the plot on the left, we show this famous plot from the Planck collaboration when they want to constrain omega n and omega k energy densities, but there is this famous degeneracy that is broken very well by the BAO distance measurement. So here on the right, it is just let's say a consistency check when the equation state for dark energy is assumed to be constant. And just to show you that if you compare VAO, supernova, and CMB alone, the BO are really constraining probe. So it's an important measurement that is helpful in cosmology. But today I want to take a step back and to discuss what Baryon Acoustic Oscillations are and how we can exploit them. So in the standard picture, in cosmology, we have the initial fluctuations, the gravitational potentials. They show up as temperature fluctuations in the cosmic ray of the ground, and they are measured with accurate precision, with great precision by the Planck satellite, as you see here from the power spectrum plot. At late time, the same oscillations, they shows up giving us this peak and deep feature at around 100 megaparsec in the SAGE scales. And these are called Baryon Acoustic Oscillations in the galaxy distributions, and we will discuss about this feature today and how we can exploit it. So, which scales? What is the scale that gives us this peak? The scale is called the Samurai scale and is defined as the cumulative length and acoustic waves travel until the baryon photon decoupling time. What is relevant in this quantity is geometrical, so it's independent of the primordial fluctuation parameters. And so this is one of the crucial ingredients to build a standard ruler. As I will explain in a few minutes. So what is a cosmological standard ruler? So it's an object of known size that is constant in redshift. In the context of the large-scale structure, we talk about a statistical standard ruler, because if in the cluster of galaxies, using statistical tools, we find a preferred scales that is constant in redshift, and we observe this scale at different redshift, then we can constrain the angular diameter distance, for instance. That is just a picture, a toy picture to show what happens. So if there is a preferred scales, then these scales can be used to measure the angular diameter distance, and then we can predict the angular diameter distance with our cosmological, assuming a cosmological model, and so then we can constrain the cosmological parameters. So I want to discuss, so let's start with this question. So are BAO a background problem? So if you go in the on archive and you look what the papers that use Baryon Acoustic Oscillations, you see that they are considered, the BO distances are considered as a late-time background measurement. But is that true? Not really, because we use the galaxy correlation function, And this is, of course, is given by the primordial fluctuations, depend on the background cosmology, depend on late time nonlinearities, and also change or can change if you have no standard cosmologies, etc., astrophysical effect, etc. So the old idea is that the peak scale is equal to the sun horizon scale. However, and this can somehow be okay, but if you want to do precision cosmology, then this equivalence starts to break down. So for this reason, now BO distances are measured in the following way. So usually, we measure in the galaxy distribution, we measure position of galaxies in terms of angles and redshift, and then we are allowed to assume fiducial cosmological parameters, and then in this way we can map from angles and redshift to co-moving fiducial coordinates. And because of this assumption, we are affected by the Alpha-Patinsky distortions, and this means that a sphere in the right cosmology will look like an ellipsoid in the wrong cosmology. So these distortions can be computed, and so for the galaxy correlation function, and as you see here, SF means fiducial coordinate. So the distorted or measured correlation function is equal to the true correlation function through these alpha parameters. That is called the isotropic shift, and is defined in terms of dV, that is just a definition in terms of the angular diameter distance and the Hubble parameter. And we call this BO distance, and that's what we are after today, not just today. Okay, so again, the Alpha-Patinsky equation. And so we want to estimate alpha, but we want to do this in a way that is background model independent. But we should be careful, because on the left-hand side we have the data, on the right-hand side we have model or theory. So we should be careful not to introduce some dependencies in this treatment, given our goal. So before moving on, let me stress again how BO are relevant and how much the community trusts this measurement. So it's just a couple of sentences that I found in some papers. When it's written that perhaps there is a difference, if you want to constrain omega k, for instance, from the CMB data, there is difference if you use different Planck likelihood, but it's not really important, because this difference is completely overwhelmed by using the BO distances that are really reliable. So today I want to discuss this, and I think it's important to understand how much we can rely on BO and what that means. So yeah, another question is how cosmology independent BO distances are. So in practice, you will find in the literature that BO distances are employed to constrain any cosmological model. So the implicit assumption here is that the BO distances, the inference is done when we want to estimate distances without assuming cosmological model, specific cosmological model. So the question is, at what level is this true? Okay, so that slide I showed before, that's the Alpha-Patinsky equation. Let us remember that we want to estimate alpha in a way that is background model dependent, and as I said, we should be careful in the theoretical treatment because at least since 20 years now, 15, 20 years, people discover that there are late-time nonlinearities, such as linear gravity, redshift distortion, scale-dependent bias, that distort the correlation function in a way that we cannot neglect. Indeed, we see here that the dashed line is the linear prediction, and you see that the continuous lines are linear prediction, and they're not compatible. Okay, so now, given what I told you, we can I can show you what happens, and using what I call the minimal correlation function model, that is basically the correlation function model that people use for BAO. It's a correlation function model that grasps the main phenomenology, and is probably the first one, it's the simplest one. There are much more advanced, accurate models nowadays. But to understand the logic, this is the very good starting point. Then you can take what I'm saying and apply to whatever model you want. So the nonlinear correlation function is related to the linear power spectrum that depend only on the energy densities, omega baryons, omega Kodak matter, and scalar spectral index. This A parameter that is scale dependent but time dependent from CDM, quintessence models, and we don't have to assume flatness. It is sigma naught that is relevant for the damping term that dump the BAO at late time. So this depends on the growth, and the energy model, on the curvature, on the tracer. So what do we do? So that's visually what we have. So we should marginalize over information we don't want to retain, like the dark energy. So the amplitude and the smoothing, for instance, depend on the dark energy. And so then we want to marginalize over those. Alpha is what we are after. And so the shape of the correlation function depends on omega B, omega C, and NS. So what do we do with those? Okay, so what we did is the following. So we vary all the parameters. And this way we can properly estimate dV. But we found that dV is estimated with a very large error, around 100%. But then if you change your variables and then you project this to the RD and dV, and RD depend on the energy densities, then you find that they are very similar error and they have a very high correlation coefficient. And so the ratio between the two is a very well constrained parameter that is constrained around 1-2%. That's good. That's what is interesting, allows us to use this tool. And so in this way, we understood we can obtain cosmological distances that are geometrical, so independent of the primordial fluctuation parameters. They are dark energy model independent, so we don't have to assume non-CDM or specific quintessence model. They are spatial curvature independent, and they are also tracer independent. We name those purely geometric Baryon Acoustic Oscillations. What is not clear is included or excluded here is modified gravity cosmologies. There are different modified gravity. Usually a new scale enters in the game, where this scale is close to the BO or not, depending on the model. Or if you have dark energy, dark matter coupling, for instance, again, depending on the model, or etc. So now let me discuss what is called the BO only, that is the standard methodology to derive this, to infer distance measurement. And then I will discuss the DAISY that is similar to this one. That's it, the historical one of the first. So what is used is called the template fitting, where here now there is the minimal model of the correlation function I discussed before. And so the parameters, the cosmological parameters are kept fixed. There is omega, the energy densities, NS, and sigma naught are kept fixed. This broadband term is added, and this was selected among 3 or 4 of proposal based on the body simulation and requiring that the result is unbiased. So what we are after is alpha, and the only parameters that are varied here, and marginalized over, is B, the amplitude here, A1 and 2 and 3, that enters in the broadband term. So the broadband term is meant to model somehow residual unknown nonlinearities and observation systematics, and to propagate uncertainties that are not propagated because of this parameter fixing. So, but because of the cosmological parameter fixing, so a prescription was introduced, and that's how the sound horizon enters. So based on simulation close to the fiducial model, it was discovered that if you multiply by RD fiducial over RD, this prescription gets you an unbiased result. So then the question is, given this prescription, this assumption, are errors on alpha properly estimated? Okay, so there are 2 problems here. The first is the parameter fixing problem that I just discussed. And then there is another more serious problem. This is the correlation function model. So because there is no, given a cosmological model, there is no a unique prediction for the galaxy correlation function. So then both 1 and 2 can have some influence on the inverse that we are doing when we estimate the BO distance. So problem 1, the parameter fixing. So then what we did, we compared the correlation function model fitting, where we vary all the parameters, with the standard BAO that fixed parameters. And with the Fisher matrix investigation, we found that the error bars of the standard BAO are underestimated by up to a factor of 2. But okay, this in principle can be addressed. With MCMC, it is much more complicated, as we will just mention later. But there is another, as I said, more trivial problem. Which galaxy correlation function theoretical model should we use? Okay, so what is the state of the art of the modeling of the two-point correlation function? So to model nonlinearities, we use numerical approaches for which we have first principle embodied simulation, meaning that they are convergent, given the result that we are interested, like the two-point correlation function. We use dark matter halo identifiers, like friend, spherical over density, Ross star, etc. They are too slow to run MCMC for data analysis, even if there is this attempt to use machine learning to speed up the computation, but for now not really for geo distance estimation. But the real problem is galaxies. So we don't have first principle simulation for galaxies because we lack a complete predictive theory for galaxy formation. So for this reason we use prescriptions like a halo computational distribution prescription to decide how many galaxies fit in a halo. So how do galaxies precise accumulated matter field? We don't know. So for these reasons, what is used is an analytical correlation function, for analytical correlation function of galaxies, but there are different prescriptions. We have to add extra assumptions to model the following effects, like nonlinear gravity, phase distortion, galaxy bias, how many parameters, in which range of case this model is working. So the reference to validate, since all these uncertainties, a specific model, is to use embodied simulations plus galaxies in halos. What that means, what is the meaning of validating a model? It's a difficult question. This is a very, let me sketch here a few questions. Like, we should decide if you want to use like fluid equation to model correlation function. We should decide which starting equation we want to use. So we use like the most famous example, standard perturbation theory, effective theoretic structure, etc. Which perturbative, we usually use a perturbative expansion. So which perturbative order we stop, one loop, two loop, etc. Can we predict the range of scales? I mean, this is not predicted, so we have to, take a simulation with some parameters and decide that at some point there's a bias and we stop and we select the range of scales. So parameters are quantities that need to be measured from the data. What is the meaning of fixing them or putting very strong trial on them? So we can just estimate other parameters best fit and errors. Can we select parameters by using model selection? We need to be careful because some parameters can have a physical meaning. So what is the meaning of selecting parameters in this context? So to address this problem, the only rule that is basically used is to requiring that we get unbiased result with respect to survey mocks. But my question is, what about the error estimation? So the error estimation is, of course, important. So here is just it's a forecast paper for Euclid, where they assume as a true model omega k WCDM and analyze this as flat round CDM. So here AP and DB are just a combination of the angular diameter distance and the Hubble parameter. So because the model is wrong, we get that the best fit is biased, as we see here, but the tension is given also by the size of the errors. And so if we are wrong in determining the error, we can go from strong tension to mild tension and vice versa. So that's important, of course. So let me now go to problem 2, that is the correlation function model. So there is a way that was probably mentioned by people several years ago, that is the following. This idea is the first idea of using the DAO, that is, using a scaling correlation function, that is if we have the offset correlation function in linear theory, so the linear approximation, is equal to the matter correlation function through this scale independent but time dependent parameter, from CDM with essence having the depth of flatness. So if we find a preferred scale in the correlation function, this will be time and model independent. So then we can measure dV in a model independent way. Okay, so a few years ago, taking a closer look at the correlation function in the bioscales, we found, of course, the peak, but we saw that there is also a dip at smaller scales, and so we define what we call the linear point, that is nothing but the midpoint between the peak and the dip, and we found that it has interesting features. So the geometrical point, independent of the model fluctuation parameters, is weakly dependent on nonlinearities at the 0.5% level. So both properties 1 and 2 can be exploited to measure distances, cosmological distance, in a way that is at some level background independent in the context of the purely geometric video, as I discussed before. Okay, so how did we get to this? So from our own plot, meaning that when we started this investigation, we didn't know how the video analysis was done. So then but we knew that the amplitude was not relevant, so we divided by the growth factor at different redshift, and we saw that all the lines were going through this point. And so then we start asking if we understand what that means, and more in particular, if we can exploit this feature to measure video distances. And so we end up taking the Ankel-Paczynski equation, it can be written this way, using this variable y. So now what's the point? The point is that on the left-hand side, on the data, we can use a model-independent parametric fit, or whatever model-independent fit, there's no cosmology there, where you estimate the peak and the dip and the linear point. On the right-hand side, since it's a linear scale, we can use the linear theory prediction, like the Boltzmann code, Campbell plus, and that we think we understand much better. And so then, then we compare the two, and in this game we are not fixing parameters, and there is no fiducial cosmology independence. Okay, so then what we want to do, we want to apply this to real data. We're curious to know what happens. So we asked the Bosch collaboration the low Z and C mass galaxy sample, and we measure the linear point, the distances with the linear point, and we compare it with the standard video approach, and we found a consistent result with a smaller error that is always convenient. So what about the validation of the linear point? The linear point, I mean, wherever you use data, you usually do some validation of your estimators. So now the theoretical input is much weaker than what I discussed for the standard video before. We want to use a smooth differentiable function. That's the theoretical input. We don't have a unique estimator. For simplicity, we use a polynomial estimator. We can reduce parameters because polynomial parameters, they don't have physical meaning. We can change range of scales. Also, there is no physical meaning here. We should be careful that the polynomial should fit the data well, so it should be unbiased. We are limited by the embodied convergence and by the 0.5% uncertainties in the bias that I mentioned before. And what about priors? So when we did the investigation with the Fisher matrix for the correlation function model, with the correlation function model fitting, using the Fisher matrix, we don't put informative priors. This can be unphysical because we have several parameters and we have one function. So then the priors can go beyond what is accepted. So then with MCMC we can enforce physical priors, like for instance, say, we can say that omega n is not negative. So, but it's tricky not to use other observable priors because with the preliminary investigation we saw that Campbell class start breaking if you go far away from the Planck. So the linear point use a polynomial parameters, they don't have physical meaning, okay, so there is no problem. And also we do conditional cosmological analysis. For instance, if the linear point is detected, we know that NS is larger than 0.5. So now, let me discuss this plot. This is what is called the Kennedy detection with the BAO. What that means that you assume the Friedman equation. You assume the Friedman equation, you take omega k as a free parameter, and then you take a bunch of BO distances of different redshift, then we put them together, and then we draw this posterior. So then you see here that at 3 sigma, you get to parameter values that are far away from the Planck best fit here, and so from the Plankton tools as well. And so, but we should be careful because all the pipelines and body simulation, wherever we use to validate our analysis, is done here, basically. So this is a nonlinear extrapolation that we don't know if we can trust. So this brings us to the following point. So what is the expectation that we have when we use BO distances? That it should be flexible enough to be used for many purposes. For instance, like energy detection, inverse distance ladder, tensions, tensions, BO consistency test. So it's possible to use only one BO distance. So how wide the parameter range should be? So if you use just one, of course, the contours will become much larger. So then the answer is the widest possible if you want to be really flexible. So is a warning. So far I've been discussing the BO distances without the BO reconstruction. BO reconstruction is a crucial tool that is used in all the official BO release since the beginning, basically since 2008. So the idea is the following: that in the late time, because of linearities, all the information, the full information is not in the 2-point correlation function. The other information is spread in 3-point, 4-point, and point correlation function. So then, ideally, if you can send back galaxies to their linear initial position, then you can increase the signal to noise and reduce nonlinear effect. So this treatment is crucial because the errors can be smaller by up to 40–50%, so it's not irrelevant. So the algorithm input assumes some cosmology because, naively, if you want to run a simulation back, you have to assume some cosmology. So like the growth rate and the matter-gas bias are the standard parameters that are used, but there is no error propagation in this game, in particular because the parameters now are not just in the theory, but are also in the data. So then how you define a likelihood in this setup. So that's a problem, I would say. So what are the caveats, summarizing? So the standard BAO assume parameters fixed to flat round CDM close to Planck best fit in the fitting procedure. The BAO reconstruction also assumes parameters without propagating uncertainties. So in general, like for validation, covariance, for instance, we have the problem that survey mocks and body simulation that are crucial to validate our pipelines. They assume flat random CDM, that the model is assumed. And the cosmological parameters that we use in this simulation are close to the flat random CDM, Planck best fit. So we need to model nonlinear physics for a wide parameter range. So I know that everybody is waiting for this, so let me discuss now the basics, but the pedagogical introduction was relevant to understand because, of course, technology goes ahead. So it's similar. So again, what is used is a template fitting, meaning that the cosmological parameters are kept fixed. Everything starts from the galaxy power spectrum, also for the correlation function. So there is this no wiggle and wiggle split that is somehow ambiguous, but I will not discuss about this today. So the assumption is that it's written that any BO scaling information is accounted by this assumption that the wiggle power spectrum can be written as a P wiggle fixed, the parameters are fixed, and this RD over RD fixed rescaling the wave vector here. So the parameters fixed are, as before, omega B, energy densities, baryons, such called dark matter, and the scale spectral index. And so then here B and C are basically modeled using the minimal correlation function model I showed before. And D is the broadband, term that is based on cubic spline basis in Fourier space, and where the width is decided based on the fiducial values for the sound horizon. So then all the BO distances result assume BO reconstruction that I described before. So again, the issue of error propagation is still there. And so that this fiducial, this is not for the error, but this is for the bias, to check the bias of the result. So then Okay, so here the assumption here is a test that the DAISY collaboration did. So the assumption here is that true cosmology is a Planck 2018 cosmology. So then the pipeline is run changing cosmology for the Agri-Paczynski, for the galaxy spectrum template, and for the BO reconstruction. And the cosmological, the cosmological parameter here is bias and growth rate. So 4 different cosmologies are tested, and the variations on the parameters is the following. So the energy densities of baryons change at most 1%, omega C 8%, scalar spectral index 2%, and sigma 8 7%. So again, there is the issue of the wide parameter range that is not taken into account. So this is cosmology here. Okay, on the left is the famous plot where you combine BAO, CMB, and supernovae, and then you see that you get a detection for dynamical dark energy. But we should be careful because when we fit when we want to estimate BO distances, we assume a model has matter perturbations plus background. So matter perturbation can be different if you have modified gravity, if you have known quintessence models, like for instance if you have the energy clustering, there is a sound horizon scale, that is a new scale, so what happens to the BAO, or if you have dark energy, dark matter coupling, etc. So here is the energy detection plot, where it is a 2 sigma, so at 2, 3 sigma you see that omega k goes up to 0.3. So again, the wide parameter range is not consistent with the fiducial test. So what are the challenges to lambda CDN from the BAO? So did we detect dynamical dark energy, or is a flat lambda CDN consistency test? So because we fix parameters, perhaps it's a flat lambda CDN consistency test. A weird one, because of course we put like galaxy clustering, supernova, and CMB. So what happens if you have like simulated data and we run the same test? I don't know. And then this of course is always related to the vanilla flat lambda CDN. But what about lambda CDN when you have neutrino mass of omega k is a parameter that we should fit to the data? So the contours will change, will become larger, of course. Okay, so let me ask this question. What do we learn about cosmology? So the aim is that we want to test cosmological models with galaxy clustering. So when we compare data versus theory, we are testing cosmological models assumptions. So this will be easy or well-defined if from a cosmological model we have a unique galaxy correlation function prediction. This is not the case, so we have to add extra assumption if we want to use the correlation function model. So when we compare data versus theory, we are testing the cosmological assumption and the galaxy clustering model assumption at the same time. So what are we learning about cosmology? That's a legitimate question. The real point is just an attempt to reduce the non-cosmological assumption, and is a more data-driven approach. So why, the real point? So as I said, the correlation function, the analytical correlation function has many unknowns, so we don't really know how to model in a unique way to linear gravity, resistivity, distortion, halo bias, how to put gases in halos, and in terms of scale is working. So when we use survey mocks, we can ensure that we get unbiased result, but what about the error estimation? Are we doing parameter estimation or mock and data consistency checks? The other point is a new theoretically defined observable, is the peak deep midpoint. Because of this simple definition, we can use a model independent estimator where we propagate all the uncertainties and we are limited by the embedded systematics. The problem that is there for everyone, let me remind this again, is that we have first principle simulation for dark matter, but what about galaxies? We don't have first principle simulation for galaxies, so predictions is complicated. So finally, are we accurate enough? So, I mean, the precision of ongoing future experiment will be very, very precise, below 1%. So, here in the last years, we collected different tests, different let's say tests. I mean, we found this result along the way. So here, for instance, is these two simulations that are called Abacus Cosmos Emulator, but they are both simulation with the same cosmological parameters. We are combined in this paper to do to test the standard BAO analysis. So when we wanted to use those, we found a discrepancy between the two sets. Those halos were different. This is because of the force softening. Force softening is a bit different between the two. So what we found is that the linear point in the two sets is in tension around 2-3 sigma. So here, also in different simulation, so the linear point has still 0.5% correction because there is a secular shift of 1%, but in some simulation can be 1.5%. So, I mean, okay, why? And here, this is the Nuni and Quixote simulation for lambda CDM, and we saw here the deep, this deep linear point and peak position, and so the deep here and here, the simulation are very similar parameters. We just map the difference 0.5% after this correction. We check the consistency between the deep here, and they are not consistent at more than 3 sigma. So can we claim we control systematics at the 0.5%? I would say that we are 1%, 2%, but it's a difficult assessment. So finally, let me conclude. So what are the challenges to use BAO distances? So the cosmological applicability of standard BAO distances is clear. So perhaps we are just performing a flat incident consistency check. So for these reasons, we introduced the purely geometric BAO, that is a framework where we can estimate distance measurement in a way that is independent of some cosmological background model. So in practice, we find two ways to deal with this. The first is the correlation function model fitting, where all the errors are propagated. With this tool, we tested the standard BAO, and with the preliminary Fisher matrix investigation, we understood that we found that the errors of the standard BAO are estimated by up to a factor of 2. So, but still there is the uncertainty. So which model do we use for correlation function? Which parameters? How many parameters? Which in this case is working? So we found a complementary approach that is somehow convenient because it does not force us to assume a correlation function model. We can be correlation function model independent. So there is a lot to do with this Euclid project we are working on. We should explore the wide parameter range. We should include with the linear point the quadruple information. We should deal with observational systematics and combine with other observations, and etc. Thank you.
Thank you. Time for questions.
Thank you for the nice talk. The BAO peak has a precise physical meaning. What is the physical meaning of the linear point?
My question is that relevant? That's when we started this investigation, that was the question that we asked. We should be careful because first, the peak is related to sound horizon, but we know that even linear theory is not the sound horizon at 1%, for instance, right? So then it's closely related. This was convenient, but now people don't use the peak. So I mean that's one of the answer. The first point is the following: that what is relevant to have a standard ruler, that standard ruler I introduced before, it is an object of known size that we constantly redshift, whatever. I mean, that's in linear theory, you have that if you have a feature in that idea of pivots, you have a feature in the correlation function. Linear theory is constant in redshift, and it is geometrical, so it's dependent on the per-model fluctuation parameters. So then you can exploit it.
So you assume linear theory.
Sorry?
You're obliged to assume linear theory.
No, okay. So we test it, right? So if it's not linear, then you have the nonlinearity shift the peak much more than the linear point. So shift everything. So then the point that we tested that in linear theory, the correlation function agree with the nonlinear prediction if you care about linear points. So it's, we tested it. That's an assumption.
Yes.
Thank you. At some moment you presented a template for the two-point correlation function, a modified version of it, and you mentioned that it was tracer independent, which I've been kind of trying to elucidate, given that we know that the clustering of different samples of galaxies is different. So you could imagine having the same clustering of ELGs than for LRGs. So I was wondering what you meant by it.
No, what I meant is that, here in this simplified template, the dependence on the tracer enters in like A, the dependent bias, and sigma naught. So then if you can marginalize over those, and so then you are marginalized over this information. You're not independent.
Hi, very interesting approach. Just one simple question. Shouldn't you worry about the halo and galaxy assembly bias? If you believe the galaxy assembly bias is true, it's still under scrutiny, then of course there will be effect that a single component couldn't capture, and then probably would move your peak. So did you try to approach that, or not yet?
You should worry about everything. When you say that we don't have ab initio galaxy simulation, you can observe people in the last 20, 30 years, like starting from Kaiser in the 84, and he broke the people's assumption that galaxies are just a random sample of the matter field. From there, people have been ahead for years and finding every few years a new effect. So where we stop? If you don't have like a Boltzmann code for the CMB, there is no stop. You don't know where to stop.
Yes, and what about your accuracy? Can you still achieve the 1%?
In that sense, I don't have the answer. That's when you say, are we accurate enough? I don't have a definite answer to that. That's, I think, is. So I don't think it's worth pushing for extreme precision or extreme accuracy, because I don't think it's possible. That's my issue.
Other question? Other person? Okay, there are no more questions. Let's thank our speaker again.